Kasumigara Naval Air Station, March 20th, 1942. Test pilot Katsuzo Shima walked across the wet morning grass toward an aircraft that, on paper, was supposed to save Japan. It did not look like the Zero. It did not look like anything the Imperial Japanese Navy had ever built. The fuselage was thick and stubby, almost barrel-shaped at the cockpit. The nose tapered down to an almost ridiculous needlepoint, with a small spinner sitting half a meter ahead of the engine itself. The windscreen was so steeply raked, so curved, that pilots later said it bent the horizon like the bottom of a drinking glass. Mitsubishi's draftsmen had spent 2 years arguing over every centimeter of that fuselage. The goal was simple: speed, climb, more speed, get to altitude before the bombers got there, hit them, come home. This was the 14 Sure Local Interceptor. It would enter service as the J-2M Raiden. The Americans would later codename it Jack, and the man who had designed it was the same engineer who had designed the most successful Japanese fighter in history, the A6M Zero. His name was Jiro Horikoshi. Shima climbed into the cockpit. He started the engine. The 14-cylinder Mitsubishi Kase radial fired through a 50-centimeter extension shaft, spinning a 3-bladed propeller out at the far end of the needle nose. The vibration rattled the airframe before the wheels even left the ground. Shima got it airborne. He flew it. He brought it back down. And then the test reports started coming in. The aircraft did not meet its speed specification. The cooling system overheated the engine. The landing gear collapsed. The extension shaft produced a vibration so severe that pilots could not hold a steady gunsight picture. The curved windscreen distorted the runway during landing approach so badly that pilots had to zigzag the airplane down the strip just to see around the nose. And the engine, designed to deliver 1,430 horsepower, had to be detuned to suppress the shaking. 15 months later, on June 16, 1943, a test pilot named Lieutenant Hoashi Takumi lost control of a J-2M2 just after takeoff. The aircraft struck a barn. He died when it caught fire. The investigation that followed would discover that the elevator control was being physically pushed forward by the retracting tail wheel. The most promising interceptor design Japan ever produced was killing its own pilots on the ground before it had fired a shot in anger. To understand why, we need to go back to October 1938. We need to go back to the moment a junior engineer in Nagoya was asked to do something no Japanese designer had ever been asked to do. We need to go back to the decision that would chase the Raiden for the next 7 years and turn an aircraft of brilliant promise into one of the great might-have-beens of the Pacific War. A decision made in pursuit of one thing and one thing only: speed. Part 1. The Bomber That Never Came. In 1938, the Imperial Japanese Navy had a problem most of the world did not yet understand. They had Zeros. The A6M Zero was the most maneuverable carrier fighter in the world. It could turn inside anything the Allies had. It could fly 1,500 miles on internal fuel. It could climb, fight, and disappear into a horizon that no other fighter could match. But the Zero was not built to stop bombers. During the war in China, Japanese naval officers had watched something that disturbed them. Chinese pilots, flying Soviet-supplied SB bombers, sometimes flew at altitudes. Japanese fighters struggled to reach quickly. The Zero was magnificent at altitude once it got there. The problem was the climb. By the time a Zero formation reached 6,000 meters, the bombers had often already dropped their loads and turned for home. Japan needed something different. Not a dogfighter, not a long-range escort, an interceptor, a fighter built around one mission: get to altitude fast, punch through a bomber formation, land, refuel, do it again. In October 1938, Mitsubishi and the Imperial Navy began informal discussions about such an aircraft. By April 1940, the specification was formalized as the 14 Sure Local Interceptor, the Kyokuchi Sentoki, abbreviated in Japanese to Kyokusen. The numbers were brutally specific: maximum speed at least 340 knots at 6,000 meters. That works out to roughly 391 miles per hour. Climb to 6,000 meters in 5 minutes 30 seconds. Service ceiling of 11,000 meters. Endurance only 45 minutes. an armament of two 20mm cannons plus two 7.7mm machine guns with armor plating behind the pilot's seat. Compare that to the Zero. The Zero has been built for range, maneuverability, and lightness. The 14 Sure was built for the opposite: speed, climb, firepower, armor. The pilot would now be protected. The range would be cut in half. The aircraft would not need to dogfight. It would need to slash through bombers and disengage. This was a fundamentally alien concept in Japanese fighter design. Every Japanese fighter built before this point had emphasized turning combat. The 14 Sure specification said, in effect, throw away the playbook. Only one company responded to the specification: Mitsubishi, and Mitsubishi assigned the project to the man who had just completed the Zero, Jiro Horikoshi, age 36. Horikoshi was not a flashy man. He had been born in Fujioka, Gunma Prefecture, in 1903. He had graduated from the New Aviation Laboratory at the University of Tokyo. He was thin, slightly stooped, and chronically overworked. He suffered from poor health throughout the war. According to his own diary, published in 1956, he was strongly opposed to Japan going to war with the United States. He wrote that when he learned of the attack on Pearl Harbor, he and his colleagues at Mitsubishi found themselves embroiled in a war they had not foreseen and did not want. But he was an engineer, and in 1940 he was given a specification that, by his own later admission, was harder than the Zero, because the Zero had let him optimize for one philosophy: maneuverability above all. The 14 Sure forced him to optimize for the opposite: straight-line performance above all. And Horikoshi did not have the luxury of choosing a clean-sheet engine. The Japanese aircraft industry in 1940 had exactly one engine in the right power class that was already in production: the Mitsubishi Kase, Mars in Japanese, a 14-cylinder, two-row radial that had been developed for the G-4M attack bomber. The aircraft the Allies would codename Betty. The Kase was big, 42 liters of displacement. Its frontal area was enormous. Drag in straight-line flight is exponentially related to frontal area. Horikoshi understood this better than anyone, and so, sitting at his drafting table in Nagoya, he began to make a series of design decisions. Each one of them was, in isolation, defensible. Each one of them sacrificed something for speed, and taken together, they would produce an aircraft that would haunt his career for the rest of his life. The bomber threat that prompted the 14 Sure never arrived from China. The bomber threat that would actually destroy Japan, the Boeing B-29 Superfortress, would not appear in Japanese skies until June 1944. Horikoshi could not know this in 1940. He was designing an interceptor for an enemy he could only imagine. And what he could not yet imagine was that the very design choices he was about to make, in pursuit of speed against that imaginary enemy, would mean that when the real bombers finally came, his interceptor would not be ready to meet them. Why am I telling you this? Because the speed obsession is not a metaphor. It is a chain of specific engineering decisions. Each one cost time. Each one cost lives. And the first of them, the one that became the visible signature of the J2M Raiden when it finally appeared, was a decision so unusual that other engineers around the world looked at it later and asked the same question: why did he do that? Part 2. The needle nose and the blind pilot. If you look at a photograph of the J2M Raiden today, the first thing you notice is the nose. It is not the round, bulky nose of a normal radial engine fighter. It is sharp, almost pointed. The propeller spinner extends forward of the cowling like a spike. Behind it, the cowling tapers back into the fuselage with no clear delineation. It looks, as one historian wrote, more like an air racer than a fighter. That nose was Horikoshi's first speed decision, and was the decision that broke everything. The problem he faced was geometric. The Mitsubishi Kase radial had a diameter of approximately 1.34 meters. If you mount that engine in a fighter the way every other radial engine fighter mounts its engine, with the propeller bolted directly to the crankshaft, the entire front of your aircraft has to be at least 1.34 meters across. That is a wall of air resistance. Horikoshi's solution, brilliant in concept, catastrophic in execution, was to move the engine backward inside the fuselage. He pushed it back about half a meter. Then he connected it to the propeller using a 50-centimeter extension shaft running through a long, tapered nose cowling. With the engine set deep inside the fuselage, the cowling could now be shaped to a much smaller diameter at the propeller, then flare smoothly outward to meet the wider body where the cockpit sat. The largest cross-section of the aircraft was no longer the engine. It was the area around the pilot. This was, on a piece of paper, exquisite. The frontal area was minimized. The drag coefficient came down. The calculated top speed went up. But moving an air-cooled engine backward inside a tight cowling creates an immediate problem. Air cooling, as the name suggests, requires air. Lots of it, flowing over the cylinder heads, carrying away heat. A normal radial engine sits in the wind. Horikoshi's buried Kase did not. So he added a mechanical cooling fan, driven off the engine itself, sucking air through the narrow nose intake and forcing it over the cylinders. The Focke-Wulf 1.9. And Germany used a similar trick. It worked, sort of. The fan rotated at high speed. The engine vibrated at its own frequency. The extension shaft transmitted torque between them, and somewhere in the harmonics of that system, something went wrong. The first J2 M1 prototype, built between February and March of 1942, was rolled out at Kasumigaura and flown on March 20th. The test results came back almost immediately. The aircraft failed to reach its specified speed. The aircraft failed to reach its specified climb time. The constant speed propeller governor was unreliable. And worst of all, when the engine was run at high output, it produced what one report called heavy vibration. The kind of vibration that loosens screws. The kind of vibration that fatigues metal. The kind of vibration that no one wanted on an aircraft they had to fly into combat. Horikoshi was confronted directly. Was the extension shaft the cause? He denied it. According to engineers who worked with him, he denied it adamantly. The shaft, he insisted, was sound. The vibration came from somewhere else. He turned out to be partially correct. The shaft was not the only cause. The propeller blade design was contributing to the problem, with insufficient stiffness creating its own resonance. But the shaft, the cooling fan, and the propeller were now coupled into one system, and changing any one of them changed the behavior of the others. The second decision, made in parallel with the first, was just as much about speed and just as expensive. The cockpit. Pilots want to see. They especially want to see when they are landing, taxiing, and looking for enemies behind them. But a tall canopy creates drag. So Horikoshi designed a low, deeply curved windscreen on the J2M1. The pilot sat low in the airframe. The view forward, over that long needle nose, was minimal, and the curve of the windscreen itself, designed to flow smoothly into the fuselage line, created optical distortions at certain angles. The distortions were worst on landing approach. According to a January 1964 account in the Japanese magazine Maru, written by Toguchi Yuzaburo, a former member of the Navy Test Department, the ride-in was unlike any aircraft he had encountered on the ground. During full-power taxi testing, the engine was so powerful relative to the airframe that the aircraft tended to nose over. Ground crew members had to ride on the horizontal stabilizers, or dead weights had to be lashed to the tail just to keep the nose from pitching forward. Forward visibility on the ground was so poor that pilots had to zigzag down the runway. They could not see what was ahead of them. You are designing an interceptor. You want it to scramble in minutes. To reach 6,000 meters in 5.5 minutes, to kill bombers and come home, and the pilots cannot see straight ahead on the runway. Imagine yourself in that cockpit. The vibration through the controls is constant. The horizon distorts through the curved glass. The propeller is half a meter further forward than your instincts tell you. Yet on paper, on every metric the Navy cared about, the design was working. The top speed numbers, even with the disappointing prototype results, were among the best in the world. The climb rate was extraordinary. The 4-cannon armament that would appear in later versions could shred any bomber. The Allies, when they later tested, captured J2Ms using 92-octane fuel plus methanol injection, would clock the J2M3 at 417 miles per hour at 16,600 feet. That was faster than the F6F Hellcat. That was faster than the Spitfire Mark V. It was, in pure straight-line terms, a brilliant fighter. Men like the test pilots who would crash and die in the J-2M deserve more than statistics. If you find this kind of forensic engineering history valuable, hit the like button. It helps this channel reach the people who care about the real stories behind these aircraft. But here is the puzzle the Japanese Navy was about to confront. A fighter that pilots cannot see out of, cannot taxi safely, and cannot hold a steady gun sight on is not actually a fighter. It is a wind tunnel model that happens to carry guns. The performance numbers were real. The vibration was also real. And which one mattered more would be answered the hard way, by the pilots. In test flights that began in 1942 and continued for another full year, during which the Imperial Navy desperately needed an interceptor in the field, and the J-2M kept failing to deliver one. What killed the test pilot in June 1943 was not the extension shaft. It was something even more revealing about the design philosophy that had produced this aircraft. And what they discovered when they tore the wreckage apart would reveal that Horikoshi's speed obsession had done something worse than just making the Raiden hard to fly. It had made it unsafe in ways nobody had even thought to look for. Part 3. The tailwheel that killed a pilot. By the spring of 1943, 14 months had passed since the first J-2M1 flight. In any normal aircraft program, the bugs would have been worked out, the type would be in production, and the squadrons would be training. The J-2M was not in any of those places. It was still in testing. The original J-2M1 prototype, with its Kase 13 engine and its three-bladed propeller and its curved windscreen, had been judged unacceptable by the Imperial Navy's flight test pilots. The reasons were exactly what you would expect: the vibration, the visibility, the disappointing speed, the unreliable propeller pitch mechanism, which was originally electric and had to be redesigned as hydraulic. Mitsubishi went back to the drawing board. The result was the J-2M2 Model 11, which first flew on October 13, 1942. Almost everything had been changed. The Kase 13 engine was replaced by the more powerful Kase 23A, rated at 1,820 horsepower for takeoff. This new engine had the cooling fan built directly into the engine itself rather than driven separately, allowing the cowling to be shortened by 20.5 centimeters. The windscreen was redesigned, made larger and less curved. A four-bladed propeller replaced the three-bladed one. 8 individual exhaust pipes replaced the original collector ring. The flap width was increased. The cockpit was raised slightly. These were not small fixes. They were a fundamental redesign, and they were the first Japanese application of water methanol injection, a technology that would become essential to Japanese aero engines, but that introduced new development delays of its own. Even so, the vibration would not go away. Mitsubishi installed rubber buffers on the engine mounts. They redesigned the propeller governor. They modified the propeller blades. Each change reduced the shaking. None of them eliminated it. The vibration would remain a defining characteristic of the J-2M throughout its entire operational life. Pilots who flew the Raiden in combat would speak of it. Mechanics who maintained it would speak of it. The aircraft simply shook in a way that no other Japanese fighter shook. The first few production J-2M2s reached the development units in December 1942. Then, the engine problems got worse. The Kase 23A was a new engine, the first to use water methanol injection. It had its own teething problems, completely separate from the airframe issues. Trials and improvements took almost an entire additional year. The first batch of serial-built J-2M2 Model 11 aircraft did not reach the operational 381st Kokutai until December 1943. That was 4 years after the specification had been issued. But during the testing phase, in the spring and summer of 1943, the J-2M started killing its own test pilots. On June 16, 1943, Lieutenant Hoashi Takumi took off in a J-2M2 on what was supposed to be a routine test flight. Shortly after takeoff, he lost control. The aircraft pitched forward violently. He struck a barn. He was killed when the wreckage burned. A month later, a chief petty officer named Sasakibara Masao experienced what the records describe as major handling issues while flying a J-2M2. He managed to land, just barely. No one could explain what had happened to him. The mystery dragged on for weeks until a Mitsubishi test pilot named Shibayama Eisaku, flying another J2M2 at higher altitude than Lieutenant Hoashi had been flying, retracted his landing gear and felt the control column pulled physically forward in his hand. Because he had more altitude, he had time to think. He immediately dropped the gear. As soon as the wheels came back down, the control column returned to normal. Investigators tore apart the airframe. They found something that should have been caught in design review. When the retractable tailwheel folded up into the rear fuselage, the shock strut on the tailwheel assembly could come into contact with the torque tube that controlled the elevator. Under certain conditions, the strut pressed forward on the torque tube. The pilot's control column responded by being pulled forward against his will all the way to the forward stop. Nose down, full pitch authority, with the pilot helpless to stop it. Lieutenant Hoashi Takumi had been killed by a design flaw in the tailwheel retraction system. Not by anything exotic, not by the famous vibration, by a simple mechanical interference that should have been spotted on a wooden mock-up 3 years earlier. Why did it slip through? Because the team had been chasing speed. They had been redesigning the engine cowling, the propeller, the cooling fan, the windscreen, the flaps. They had been wrestling with the extension shaft and the vibration. The tailwheel was a detail, until it killed someone. The fix was straightforward once the cause was identified. A small modification to the tailwheel shock strut prevented contact with the elevator torque tube. Production resumed, but by then, another Raiden had disintegrated in midair over Toyohashi airfield, the cause never satisfactorily explained. William Green, the British aviation historian, recorded that investigators speculated either a failed engine attachment point caused secondary airframe failure or the engine cowling itself detached and struck the tail assembly. Both engine power attachment points and cowling fasteners were strengthened. Raidens continued to be lost after the modifications. Stop and think about what is happening here. The same design philosophy that produced the streamlined nose, the curved windscreen, the buried engine, the extension shaft, the cooling fan, is now producing failure after failure in the basic structural integrity of the aircraft. Each speed-focused design decision has created its own follow-on problem. Each fix has revealed another issue, and the calendar keeps moving forward. In 1943, while the Raiden was killing its own pilots in testing, American B-29s and B-24s were bombing Japanese positions across the Southwest Pacific. The Battle of the Solomon Sea was over. Guadalcanal was lost. The Japanese Navy needed an interceptor, an actual operational interceptor, and the design that was supposed to provide it was still being debugged. 6 years had passed since the original informal discussions began. 5 years had passed since the Kyokusen specification, and the speed-obsessed interceptor that Horikoshi had drawn on his drafting table in 1940 was still not safe to put in frontline squadrons. But when it finally did reach the squadrons, in late 1943 and early 1944, something happened that the engineers had not predicted, something that no amount of vibration testing or aerodynamic calculation could have warned them about. The pilots, the men who would actually have to fly this aircraft against American bombers, looked at it, and many of them refused. Part 4. The pilots who refused. In the autumn of 1943, before the J2M had even reached its primary operational unit, the Imperial Japanese Navy ran a series of mock dogfights at Yokosuka. The Navy had a small number of J2M1 prototypes available. The Yokosuka Air Corps put them up against A6M Zeros to evaluate how the new interceptor would perform. The result was a disaster. Japanese fighter doctrine in 1943 was built around horizontal maneuvering, tight turns, sustained dogfights, pilot skill expressed through the angle and aggression of the turn. This was the doctrine that had won the early Pacific. It was the doctrine the Zero embodied. And it was exactly the doctrine the J2M had been designed to ignore. The J2M's strength was energy fighting. Keep speed high, climb, dive, slash, disengage. Never let yourself be drawn into a turning fight. Use the airframe's straight-line performance, then convert speed into altitude, then convert altitude back into speed. This is the way every modern interceptor works. It is the way the F-86 Sabre fought 10 years later. It is the way every jet fighter has fought since. But it was not what the Zero pilots at Yokosuka were used to. They flew the J2M1 like they flew the Zero. They tried to turn with the A6M3s. They lost every engagement. They wrote reports concluding that the J2M was inferior. The point that the J2M's true advantage lay in energy tactics, in not turning, in fighting a fundamentally different kind of air combat, was not stressed in those reports. The aircraft was judged according to the tactics it had been designed to abandon. The wing of the J2M was small, 20.05 square meters. That is significantly less than the Zero, and the loaded weight was higher. The result was a wing loading that Japanese pilots had never encountered in a service fighter. The J2M3 came in at roughly 170 kilograms per square meter. Compare that to the Zero, which was under 110. This meant higher stall speeds, higher landing speeds, less forgiveness for pilot error. It also meant that in a sustained turn, the Zero would outturn the J2M every single time. Add to this the cockpit visibility problems, the vibration, the tendency to nose over on full power takeoff, the need to zigzag down the runway, the longer takeoff roll, the unforgiving stall behavior. Most Japanese Navy fighter pilots were not interceptor pilots. They were dogfighters. They had been trained from cadet school in the values of maneuverability and finesse. And here was an aircraft that punished those instincts. That demanded a different kind of flying, that looked, in their eyes, like a brute. Aviation historian Henry Sakida documented that many Japanese pilots openly despised the Raiden because of its lack of maneuverability. They stated quite simply that it could not survive against a Hellcat or a Mustang in a dogfight. They were correct about that. The J2M was not designed for dogfighting, but that was not the point of an interceptor. The pilots wanted Zeros. They preferred the older, slower, less heavily armed Zero because it flew the way they had been trained to fly. When the 381st Kokutai, the first operational unit to receive J2M2 Raidens, was preparing to deploy to the Philippines and the Dutch East Indies in March 1944, they were told to give their Raidens back. The unit was re-equipped with Zeros for the deployment. Why? Because of a fatal accident from an unexplained airframe failure had spooked everyone, and because the squadron's pilots and ground crews had not been trained to operate the new fighter under combat conditions. The Raidens went back, the Zeros went forward. The J2M did finally see combat in June 1944, during the Battle of the Philippine Sea. Small numbers of J2Ms operated out of Guam and Saipan. They were quickly overwhelmed. Some made it to the Philippines. Their combat debut was, to use the historian's word, unsuccessful. The 381st Kokutai eventually received a small number of J2M3 Raidens in the Celebes in September 1944. There, in combat against American B-24 bombers, they finally scored. One bomber confirmed kill, credited to the new fighter. One. This was the aircraft that, 4 years earlier, had been intended to clear the skies of high-altitude bombers. Inside the Imperial Navy, an institutional judgment was being formed. In June 1944, the Navy decided that its primary land-based interceptor going forward would not be the J2M Raiden. It would be the Kawanishi N1K-J Shiden, a different aircraft from a different manufacturer. The Raiden would continue in production as a stopgap. The new aircraft Horikoshi was working on, the A7M Reppu, was intended to be the Zero's successor, but the A7M was running into its own engine problems and would barely enter prototype testing before the war ended. The Raiden, in other words, was a fighter that the Imperial Navy itself had quietly given up on, even as it kept building them. A few pilots, the ones who understood interceptor tactics, embraced the Raiden. The most famous was Sadaki Akamatsu of the 302nd Kokutai based at Atsugi. Akamatsu had received his wings in the Naval Air Force in 1932. By 1944, he was in his 30s, a veteran of more than a decade of combat flying. He had a reputation. He drank. He fought. He punched officers who irritated him. He was said to have flown combat sorties drunk. He survived the entire war without major injury, which, in the Imperial Navy of 1945, was a statistical anomaly. Akamatsu flew the J2M3 with tail code YOD-1195. He understood what the aircraft was for. He used it the way it had been designed to be used. He claimed 2 P-51 Mustangs in that specific aircraft on April 19, 1945. The 302nd Kokutai sortied 24 ride-ins against a B-29 raid on December 3, 1944, alongside other Japanese fighters, and brought down 3 B-29s. 3. These were the rare successes. They came years too late, in numbers far too small, against a bomber fleet that would soon switch from daylight high-altitude raids to nighttime low-altitude firebombing, where the J2M's high-altitude designed strengths would matter even less. If your father, grandfather, or uncle served in the Pacific Theater, either as a B-29 crewman, a Navy aviator, or a member of a unit that fought the air war over Japan, I would be honored to read their story in the comments. What unit did they serve in? What did they say about the Japanese interceptors? The personal accounts that never made it into the history books are the ones I most want to preserve. The B-29s the ride-in was supposed to stop were now arriving in numbers that no fighter in the world could have stopped on its own. And the production lines that were supposed to be churning out hundreds of ride-ins every month were about to be hit by something even worse than a design philosophy. They were about to be hit by the bombs themselves. Part 5. Too late, too few. Total production of the J2M ride-in, all variants, across the entire war, came to approximately 621 aircraft. 621. Compare that to the more than 10,000 A6M Zeros built. Compare it to the more than 15,000 P-51 Mustangs. Compare it to the more than 12,000 F-6F Hellcats. The ride-in, the interceptor that was supposed to defend the home islands of Japan from strategic bombing, was built in a quantity smaller than the number of B-29s the United States manufactured during the war. The United States built 3,970 B-29 superfortresses. The ride-in was outnumbered before it even left the factory. The factory itself, by the end, was barely functioning. In December 1944, American bombing raids on Nagoya began. The Mitsubishi Dai Sankokuki Seisakusho aircraft plant took a direct hit. Complete loss of airframes, machine tools, and jigs. Production halted. Even when the factory itself was not directly hit, the supplier network around it was. Materials disappeared. Construction tools wore out and could not be replaced. The desperate Japanese government recruited child labor from Taiwan, bringing more than 8,400 youths between the ages of 12 and 14 to Mitsubishi plants in a program known as Shonenko. Children were now building the interceptors that were supposed to defend the empire. The aircraft they built came in too few. They reached squadrons too late. The 302nd Kokutai at Atsugi, the 332nd Kokutai, called the Rainbow Unit, at Iwakuni and later Naruo, the 352nd Kokutai, the Kusanagi Unit, at Omura, the 381st Kokutai, scattered across the southern theater, small units fighting an air war they had already lost. The improved variants Horikoshi and his team kept producing in the final 18 months told the story of a design philosophy, still pursuing the original obsession, still trying to make the J2M faster, climb higher, fight at altitudes where the B-29s actually flew. The J2M4 Model 32 with a turbocharger mounted in the side of the fuselage was supposed to maintain its rated power up to 9,100 meters. The turbocharger never worked properly. Only 2 prototypes were built. The project was canceled in February 1945. The J2M5 Model 33, with a different supercharger arrangement on the Kase 26A engine, produced perhaps the best performing ride-in of all. About 34 were built. The J2M6, the J2M7, model numbers that paint a picture of a design team chasing fixes faster than the war was running out. By March 1945, the American bombing strategy had shifted. General Curtis LeMay ordered the B-29s down to low altitude at night, carrying incendiaries instead of high explosive bombs. The ride-in, designed specifically as a high-altitude daylight bomber-destroyer, was now hunting an enemy that no longer came at the altitudes the J2M had been optimized to fight. It was not equipped with radar. It could not find the bombers in darkness. The single mission for which Horikoshi had sacrificed everything else, the high-altitude daylight intercept, was being made obsolete by the enemy's choice of when to fly. On August 15, 1945, 2 hours before the Japanese surrender was officially announced, 4 J-2M Raidens and 8 A6M Zeros of the 302nd Kokutai took off from Atsugi and intercepted a formation of F-6 F Hellcats from the carrier USS Yorktown over the Kanto Plain. In the engagement, 4 Hellcats were shot down. 2 Raidens and 2 Zeros were lost. It was one of the last aerial combats of the Second World War. By the time the surviving Raidens landed, the Emperor had announced the end of the war. 2 hours. The interceptor that had been designed in 1939, that had first flown in 1942, that had killed its own test pilots in 1943, that had reached its first operational unit at the end of 1943, that had made its combat debut in June 1944, that had been judged inferior by the Navy in 1944, that had been built in pitiful quantities through 1945, scored its final victory 2 hours before the war that had created it ended. Here is the forensic verdict. The J-2M Raiden was not killed by any single decision. It was killed by a philosophy. Speed above all. Speed at the cost of visibility. Speed at the cost of cooling. Speed at the cost of stability. Speed at the cost of pilot comfort. Speed at the cost of buildability. Each individual choice could be defended on aerodynamic grounds. Each one was, in isolation, the choice a brilliant engineer would have made. Jiro Horikoshi was a brilliant engineer. He was probably the most brilliant aircraft engineer Japan produced in the 20th century. But brilliance is not the same as wisdom. And the speed obsession that had served Horikoshi so well on the Zero, where speed had been balanced against 6 other priorities, became a kind of tunnel vision when the 14 Sure specification told him to ignore everything else. The Zero had been a synthesis. The Raiden was a maximization. One aircraft was a balance. The other was a bet that everything else could be solved later. Everything else could not be solved later. The extension shaft fought him. The cooling fan fought him. The propeller fought him. The visibility fought him. The tail wheel killed Lieutenant Hoashi Takumi in 1943. The vibration never went away. The pilots refused to fly the aircraft in the way it was designed to be flown. The Navy gave up on it as a primary type while it was still in production. Horikoshi knew. After the war, he would write about the Zero in his memoir, Eagles of Mitsubishi, published in Japan in 1970 and translated by the University of Washington Press. He talked about the trade-offs of fighter design, about the difference between optimizing for one thing and optimizing for the whole. He had lived through the J-2M. He understood by then what had happened. He had been on the wrong side of his own design philosophy. His next attempt, the A7M Repu, would never enter mass production. The war ended before it could fly in numbers. Horikoshi went on to help design the YS-11 civilian airliner. He taught at universities. He received the Order of the Rising Sun, 3rd class, in 1973. He died on January 11, 1982, age 78. There is one surviving J-2M Raiden in the world today, a J-2M3 Model 21, serial number 3014, on display at the Plains of Fame Air Museum in Chino, California. It was built at the Mitsubishi Nagoya plant. It served with the 302nd Kokutai at Atsugi. It was captured by American occupation forces. It was shipped to the United States for technical evaluation. It was passed to a trade school in Los Angeles. By 1952, it was a tourist attraction at Traveltown and Griffith Park. In 1958, it was donated to the museum where it sits today, the sole survivor of 621 aircraft. The sad thing about the Raiden is that the design, in its later variants and on its best days, was good. It was very good. When the Americans tested captured J-2M3s using high-octane fuel and water methanol injection, they clocked them at 417 miles per hour at 16,600 feet. World-class performance. The 4-cannon armament was deadly. The climb rate was extraordinary. In the hands of a pilot like Sadaki Akamatsu, The Raiden could engage and defeat American P-51 Mustangs. It could climb to bomber altitude faster than almost any contemporary fighter in the world. The aircraft was not the failure. The story was. The story of an engineer chasing one number while ignoring the others. Of a Navy that wrote a specification narrow enough to break the man who tried to fulfill it. Of a 4-year delay between specification and combat, during which the war Japan was supposed to be fighting changed shape 3 times. Of pilots who refused to fly the airplane the way it had been designed to be flown. Of test pilots who died learning what was wrong with it. Of children riveting wings together in a factory that would be bombed before they finished. If this forensic deep dive into the engineering choices behind the J2M Raiden gave you something to think about, hit the like button. It helps this channel reach the viewers who care about getting the history right, not just the version that makes it into the textbooks. Subscribe if you want the next chapter, because the men who built these aircraft, the pilots who flew them, the engineers who agonized over them, they deserve to be understood, not just remembered. The Raiden was not killed by American firepower. It was killed by a single equation that left no room for the other equations. War is mathematics, but it is also 1,000 small decisions about which mathematics matters most. The men who flew the Raiden into combat did not write that equation. They simply had to live with it, and in too many cases, die inside it. They had names. Lieutenant Hoashi Takumi, Chief Petty Officer Sasakibara Masao, Lieutenant Junior Grade Sadaki Akamatsu. The hundreds of others who flew, fought, and were lost in an interceptor that was, in the end, faster than any of them needed it to be, and ready for combat long after the combat had already been decided. They deserve to be remembered by them.